Hello, today I'm going to talk about some work that I've been doing at the University of New South Wales with Andrea Lennon and Scott Tyo about the physical channel structure of a microanalyzer array and the bounds on that physical channel structure. I'm going to go over the motivation for this work. I'm going to briefly introduce a derivation of how we obtain the physical channel structure. Detailed derivation will be in the paper. I'm going to interpret the results of the derivation, and it gives us some intuitive insight into what the physical channel structure means as compared with the parameters that we have to design microanalyzer array. Then I'm going to show some results from using a conventional linear micropolarizer array. I'm going to go over bounds and what they mean, and then why do we want to use them in future work. So this work was started from a question by Matthew Kupinski during one of my PhD committee meetings. And he asked, well, what is the physical structure of a micro polarizer array? And at the time I didn't know exactly. And then we asked, in addition to that, well, if you know the physical channel structure of the array, what bounds does that impose on when you can use it as a channel? So I'm now going to shift to the derivation. We have to make some assumptions, and we have some parameters that the array has. So this is a two-dimensional array. It's going to be an ideal physical channel structure, and we are given a pixel shape, and the pixel shape is the same for each pixel. And then the analyzer functions for the polarimetric part of the array are assumed to vary only over space. And then we have some array size, and we have to assume that when we do the spatial detector integration that the pixels are disjoint. We also assume that the Stokes parameters for the analyzer on each pixel are constant over the whole pixel array element, so constant over the shape function. We don't look at temporal integration or the effects of that here. And then we assume that the pixel array is given by a rectangular grid that's evenly spaced. So now we can begin the derivation of a single pixel element. We define the pixel shape function as h, and h can vary over x and y. And so this shape is arbitrary. It's the assumption is that all the pixels have the same shape. And so for some specific pixel at some specific location on the 2D plane, we'll denote that location x sub I and y sub j. And we can just have this shifted pixel function for some arbitrary position. And then we multiply that pixel function by the periodic analyzer functions. This is something we can choose. And then when we measure the element, we integrate over the area. Pixel shape function multiplied by the dot product of the Stokes parameter we're measuring at that pixel and the analyzer set of analyzer parameters that we have at that pixel. So if we only look at the system part, we ignore the data, then we can just have the set of analyzer parameters multiplied by the pixel shape function. And since they're linear, we can break it up and look at just the S0, S1, S2, and S3 components. And then if we ignore the spatial integration, then we just have this equation here. Now, to look at an array, we can just add over the pixels, and we can do this because we assumed that the pixels are disjoint. They don't overlap one another in space. And so we can get this expression, which is pretty simple. And then to obtain the physical channel structure, we take the Fourier transform of this. The Fourier transform of the pixel shape function, some arbitrary shifted pixel shape function, goes to this. It's the some sinusoidal term multiplied by the Fourier transform of the pixel shape function centered at 0, 0. And then when we can go through some algebra, and we obtain this expression here. We have the pixel shape, the Fourier transform of the pixel shape function multiplied by the double sum of some sinusoidal terms, and then multiplied by analyzer parameters at each specific pixel. We can change notation to make this look more like a Fourier series. It's not a full Fourier series because we have a finite summation here. But if we put in the pixel pitch, p sub x and p sub y, then we can get any kind of array in this expression here. Like I just said, this thing here approximates the Fourier transform of some function. Now we can pull the individual components of the analyzer out front. That's what the k's denote. So then we can just look at the effects or the physical channel structure of each specific analyzer element that we're using. What does the math above imply? We can do a little bit more analysis. The physical array has some unit cell or superpixel geometry shown here. We have some number of superpixels or unit cells, and then we have the specified analyzer elements within the unit cells. We assume these are periodic. This is showing the conventional linear micropolarizer array, and we have 4 different linear polarization parameters. Now, what the math tells us is that we can completely characterize any microanalyzer array given the assumptions we made by the pixel shape. So here we've assumed that it's a square. The number of unit cells that you have in the x and the y directions, they don't have to be the same. And then the unit cell geometry, so what the unit cell itself looks like and how it's laid out and what analyzer functions are in each unit cell element. The mathematics shows us that in the channel domain we can completely describe the system by these 4 parameters. I'm going to show some results using a conventional linear micropolarizer array. We take the Fourier transform of the pixel shape. Of course, we just get a sinc function. So here's the center lobe of the sinc. These axes are in frequency per millimeter, spatial frequency. And we have here, we've assumed a square pixel. It's 9 by 9 microns. Now we can show some of the dependence on the number of unit cells or superpixels. Here we've assumed that the number in the x and the number in the y directions are equivalent, just so we can make the graphs easier. And so this number means that there's 2 in the x and 2 in the y direction. This graph is log-like scaled. So the scale down here is given in something that's equivalent to order of magnitude, but we have negative values. So the negative values here aren't negative powers. It means that the magnitude is negative. As we increase the number of superpixels, you can see that as we expect, our delta function approximations become more and more narrow or sharp. They also become greater in magnitude. And then we've graphed the real and imaginary parts. And that was S0. Here is S1. As we go through the number, as we increase the number of superpixels or unit cells. And S2. Remember, for a conventional linear micropolarizer array, S3 cannot be measured. What are we interested in for this analysis or for applications? We want to make sure that we have, when we use a channel definition of a system, we need to ensure that when we say we're using a delta function, we have something that really is close to a delta function. And as you can see, I've zoomed in here on the delta function approximations S1. And for 2 superpixels or unit cells, this is quite broad. And I've just zoomed in to show better the structure, and also the scale has changed to linear, and we've let the scale float. So this gives a different perspective. We can define some cost function which characterizes the sharpness of these delta functions, the physical delta functions. And here we define this cost function as the sum over the delta function locations. So once you design some microanalyzer array, you will know where the delta function locations are, and so you can index them. And then we take the double integral of this AF function, and the double integral is over some area around the delta function location. The AF function is just the function of the array, so this is just the channel structure function. And then d sub j specifies the sharpness, tolerance or sharpness that we want. And then when we compute this over n, you can compute some n at which your array will give the sharpness specification that you need. It is depicted graphically. These are the d sub j's I spoke about before. S2 is not shown here for the conventional linear micropolarizer array. It's exactly the same as S1, except these two delta function approximations are negative in magnitude. We can then specify some d sub j here. I've just used squares, and they're 16 by 16 per millimeter. And now we can see what happens graphically as we increase the number of superpixels. You can see around 10, the first lobe here of the approximate delta function crosses the boundary of our d sub j. And now here's a comprehensive graph of the cost function versus n. Here you can see it has a peak, and then we get a variation, some sinusoidal variation. And this is because as the delta function approximation crosses the boundary that we've set, there are negative lobes around the first center lobe, which decrease the integral values. But if you keep going out, then it will settle down to some approximate value and flatten. And so here, for this case, the delta sub j's that we used weren't those squares that were 16 by 16 because that's too large. For this graph, these squares were 2 by 2 per millimeter. If you look at the peak value, when we hit 56 superpixels or unit cells, then we have a set of delta functions which is sharp enough. So for this application, if we needed something that was in the 2 per millimeter range, we would just need 56 superpixels, and we've gone out to 512 here. So this gives you some bound on the number of superpixels that you need to meet some sharpness specification. Now at this point, some of you in the audience may be asking, well, the sharpness specification is determined by the array size, and this is true. We calculate the sharpness, we calculate the approximate delta functions given some array size. Now, when would this be of utility? Well, this analysis doesn't use any noise, and it also assumes that you have a perfect array. And so in a real case, you would need to have noise included. Noise will decrease the magnitude of your physical delta functions that are measured, that can be measured, and it'll also if you have systematic error, like the analyzer elements have slightly different rotations, that will also decrease both the physical and the measured delta functions. And so you can use this specification to get some value of n that you need in order to have a high enough or sharp enough delta function to come out of the noise or come out of the systematic errors that are introduced. Furthermore, there's been a lot of recent papers on compressive sensing, which tried to make the sensors smaller. And this gives you some bound on what you need to do polarization work with to get in the channel domain to obtain a sharp enough delta function if you want to make the sensor as small as possible. It also, of course, when you have a smaller sensor, it affects your field of view, but this is what compressive sensing is about. So this gives you a bound to obtain polarization information using a channel formalism. Why did we ask this question? The first answer is for curiosity. Matthew Kapinski asked this question and we did not know the answer, so we attempted to answer it. What can this type of description tell us? Well, it gave us a intuitive way to describe the delta function shape and delta function layout given the parameters of how many superpixels or unit cells you have, the geometry of the superpixel or unit cell itself, and the analyzer layout within that superpixel gives you a complete channel structure for a two-dimensional array. So if we have these parameters that we can use to engineer microanalyzer arrays, we don't necessarily need the underlying focal plane array to have the same pixel size as the microanalyzer array. So we could do some subsampling of the microanalyzer array, and this would give us some pixel shape engineering capabilities. The other thing that we could get is perhaps lower cost solutions by analyzing the needed array size systematically for something like compressive sensing application. And finally, we could engineer for bandwidth using the pixel shape and the superpixel or unit cell layout. This allows an optimal bandwidth for some specific task along with the subpixel sampling to be achieved given the mathematics and the physical channel structure that we've shown here today. Thank you.